spectrophotometry. Because this is really something that you will need all the time when you work in a lab. A lab without a decent spectrophotometer isn't a lab. It's a little bit like a house without a cat is not a home. So in this case, the spectrophotometer is your cat. And you know, if you go in the lab tomorrow and stroke it, that's fine with me. You know, as long as you treat it well. Don't try to feed it mice. Spectrophotometers don't like that usually. But we need to do a little bit of theory in order to understand what you can do and what you can't do with a spec. So the first thing that I want to emphasize to you, and for those of you who have done physics, it's really old stuff, but it's important, is that whenever we have any kind of electromagnetic radiation, it can interact with matter. And we'll come back to that in a minute, why it interacts. So for the time being, let's just simply say any kind of electromagnetic radiation interacts with matter. And obviously we know a lot of different forms of electromagnetic radiation. And just to give you just a flavor of that, let's see. What we used in the practical the week before last was basically we used visible light, and also we used UV light. All a theme on electromagnetic radiation. So the visible light usually goes from about 400 to about 800 nanometers. The ultraviolet light goes down. It's about, well, it has a shorter wavelength. We don't really worry too much about the wavelength at that point. We are just simply trying to figure out how things actually interact with matter, how this radiation interacts. And one thing is very important to note is that this electromagnetic radiation is some kind of energy. And each particular wavelength, for example here, blue wavelength, has a particular value of energy. Okay? So this value of energy for, let's say, for blue is different for the value of energy that red light has. And all these different wavelengths that we see here have very different energies. And in fact, the energy of light or any kind of electromagnetic radiation depends on the wavelength. And the shorter the wavelength, the stronger, the higher the energy. Okay, so how does electromagnetic radiation actually interact with matter? How does it do that? Sorry? It excites electrons, exactly. Now let me give you an example for that. Can I abuse you for a moment? No? No abuse? Okay, good. Can I abuse you for a moment? Okay. Okay, fantastic. Thank you very much. Can you please stand up for a moment? I need you. I need your help. Wonderful. Now, imagine I'm an electron. I'm living happily on my level here, And now some electromagnetic radiation comes along and it interacts with me. And this electromagnetic radiation has some energy. So, push very lightly. Okay, so there is an interaction there. Thank you. There's an interaction there, right? I got a little bit of energy. Yeah, that wasn't strong enough. I'm just sitting here on my level, you know. I'm minding my own business. Now push a little bit stronger. Aha. Wasn't still. What? Yeah. Excellent. Now I got exactly the right level of energy from this light. From this electromagnetic radiation to jump up to the next level. And remember, the electrons, they have very discrete levels. So it has to have exactly the right level of energy. Push more. Right? If I don't have the right level of energy, I just do all sorts of weird and wonderful things. Right? Thank you very much. You've been a fantastic radiation. Yep. This is how how electromagnetic radiation interacts with matter. It shoves the electrons to a next, more comfortable level. What happens then? Electrons are up there. And then? Aha! They release the energy again. They jump down. How do they release the energy? Sorry? Through heat. Or they send out light again, which is called fluorescence. But they usually jump back onto the next level. So that's actually how radiation interacts with substances. Okay? Now here's probably a very stupid question for you biologists. Got here a leaf. What color? Green. Why are leaves green? Chlorophyll. Mm-hmm. What does the chlorophyll do? It absorbs energy, yeah? And it absorbs, obviously, light, because that's the energy that we're working with. And you said something very important. It absorbs? It absorbs predominantly wavelength that is not green. That's why we see it green. That's the one that is not absorbed. And if you look at chlorophyll, it particularly absorbs, to get this out, it absorbs in the red and in the blue. And the rest here, where it doesn't absorb very well, the combination of this one here gives you more or less green, and that is what we see. Right? Now, how come we have red leaves? What do these red leaves absorb? They absorb green predominantly, exactly. That's exactly the opposite. So they absorb green. Would you be surprised if I told you that a month ago these were red? These were green as well. So where does the red come from? Loud? Well, actually, a plant can't afford only to be, choosy and use red and blue. Buggers can't be choosers. It has to also absorb in this range here. So therefore, it has accessory pigments, like carotenoids. That's the stuff that gives carrots the color. Usually, the absorbance of the red and the blue, however, is much stronger. That's why we see it as green. But chlorophyll is a very precious thing. You want to recycle it, especially in autumn. It contains a lot of nitrogen. Nitrogen is sort of a premium for a plant. It can't afford to waste it. So nitrogen will be recycled, chlorophyll will be recycled, and it will be degraded. How exactly nitrogen and chlorophyll is degraded, we still don't understand 100%, but it's one of the most important processes on this planet. So if you want to do a PhD, there's still a lot to discover with that stuff. And what is left then, if you take away the chlorophyll, the stuff that absorbs in the red and in the blue is your accessory pigments, like the carotenoids. And that is why in autumn leaves are red. And when you have Indian summer, then it's really beautiful. So at least now, hopefully, you see how these things fit together. Here's another question for you. Okay, I need another victim. Can I use you as a victim, please? Can you stand up, please, for a moment? Stand here. I'm trying to sup you now. Right? I'm trying to sup you. Let's see. He's quite broad, so... Let's see if you absorb the energy that is transmitted from me, from my iPad, over to the screens. What do you see? Does he absorb? No. Why doesn't he absorb? Thank you very much.
I don't know.
Thank you very much. Why doesn't he absorb? It's just simply the electromagnetic radiation that I send out, that my Wi-Fi here sends out to the Apple TV down there, just simply goes straight through him. It has the wrong energy for any of the electrons to interact with. Yeah? If there is no absorbance, it just simply goes through. If I put some, let's say, thick metal plates around you or in your body, then this would absorb the energy and would block out the signal.
Metal on my leg, do you want to try that?
No, it's fine. It's fine, thank you. Don't want to inconvenience. Why? How come you have metal in your leg?
I broke my leg as a kid, so I've got tungsten pins.
Okay. Certainly not very nice for you. So when you go to the airport, it always beeps when you go through a security. Huh?
Tungsten doesn't set them off.
Oh, okay. It's tungsten. Okay. Okay, good. I don't know whether you can shield Wi-Fi with tungsten, so would be interesting, actually. No, we don't do that now. Right? So it has to have the right energy in order to interact with the matter, like with the push. If the push is not strong enough, then nothing happens. If the push is too strong, then, you might even lose your electrons. And it has to have exactly the right energy. By the way, what's the speed of light?
3 times 10 to the 8.
Speed of light is around 300,000 kilometer per second. Do you know how you measure the speed of light? Very easily. Which is pretty accurate, actually. Now you can do that at home. All you need is a bar of chocolate, a ruler, and a microwave. And if you want to do that, I probably will post a link how you can do this experiment yourself. And the chocolate won't get destroyed, so you can eat it afterwards. Right? Okay, so that is basically how electromagnetic radiation interacts with matter. How can we use this? Now, let's do a little experiment. Let's say we have a container, and in this container is a liquid, and this liquid contains little red molecules. 1, 2, 3, 4, 5, 6, 7. 7 molecules. What light is absorbed by these red molecules? What color? Green. Exactly. Let's see. So we have green light, and I draw this as a sort of a wave. 4. Now, obviously, these molecules will absorb the light. Not every single molecule will be hit by it. So let's say 2 of these light beams come out at the end. Yeah? Make sense so far? Right. What would happen if, for example, I increase the number of red dots, red molecules? What would happen in this case? Sorry, say again loud. Less light would go through. Yeah? So let me do that. So basically, bless you, what happens is really, if we look at what comes out at the back, I mean, at the end of the thing, it depends on the concentration of the red dots. We call this, what comes out at the back, basically, we call this absorption or absorbance. How much of the light is out, comes out at the end after it went through it? After it went through, oops, that should be green, after it went through this bit here. So the absorbance depends on the concentration, and I do that red, on the concentration of the material that it interacts with. Make sense? What would actually happen if I shown if I used yellow light? What would happen? What would happen if there was yellow light? Sorry? Basically, probably all of it would go through. Yeah? Why? Because it doesn't have the right energy to hit the electrons of my little red blobs. Exactly. Yeah? So we need to be exactly in the right wavelength that something happens. Right. Now, what would actually happen if I put in another container with even more of the red dots? And I shine green light on it. The absorbance will become even less again, because the light has to go through a longer pathway and potentially encounters more of the red blobs. So what we can do is we can actually now write absorbance, very often it's abbreviated as ABS, is dependent on the concentration of a substance, and it is also dependent on what is called the path length. The longer the path length, the less of the substance is absorbed. The more of the light is absorbed, right? The higher the concentration, the more of the light is absorbed. Now, if we've got something like that, where two things determine something like the absorbance, we can write it as absorbance is directly proportional to the concentration times the path length. Very often, path length is abbreviated as D, distance. So absorbance depends on concentration and the path length. Now, obviously, this thing here, this is proportional to, it's horrible. Mathematicians don't like that. They want an equal sign or nothing. So how do we convert this, the wave, into an equal sign? Well, we actually just simply use a proportionality factor. And then, are you whinging or is that? No. Oh, it's the chair, isn't it? Oh. Oh, it's the desk. Oh, sorry, I thought you were in pain. My dog does that when he wants food or so. Sorry. So absorbance equals the concentration of the substance times the path length times this proportionality factor, and this is called epsilon. Epsilon. And this is usually called the extinction coefficient. Extinction coefficient. This is this epsilon. Now, what does this epsilon actually depend on? It depends on the right wavelength. So epsilon depends on wavelength. So in our case, green light and red blobs, they absorb very well. Remember, red blobs and the yellow light, they don't absorb at all, the yellow. Well, mostly not. So in this case, this is where the wavelength comes in. The extinction coefficient might change with temperature. And it also might change with what is called the pH. So whenever we do an experiment where we measure absorbance, we need to be very, very clear that we have to do that under very defined conditions. Yeah? Now, this thing here that I've just written down, absorbance equals concentration times d, the path length where the light has to go through, times epsilon, the extinction coefficient. This has a special name, and this is exactly, you are absolutely right, it is the Beer-Lambert law. And this is something that you need to know. Absolutely, that's not negotiable. Every biologist needs to know Beer-Lambert. Yeah? Now, question for you. Does the Beer-Lambert law, as it is written, does it have explicitly the wavelength in it? No. Right? And I say that for one reason. I say that because even in the final year, students are sometimes trying to do very interesting things. They can't remember this very important Beer-Lambert law, and they just say, oh, it had something to do with wavelength, didn't it? So actually we multiply with the wavelength. And you think, no. The wavelength is inherently built into this epsilon here. Yeah? So you don't touch the Beer-Lambert law with the wavelengths. It is already in this epsilon. So under no circumstances ever would you need to multiply anything with the wavelengths. Okay? Are you happy with that? Right. Now let's have a look at, I have a sort of a fetish. What? It's units. Right? Let's have a look at the units that we are dealing with here. Absorbance equals C times D times epsilon. Let's try to figure out what units we have for the different things. Now the absorbance is basically, it's a dimensionless unit. It has no unit. Concentration. What is the unit for concentration? Loud? Moles per liter, for example. What is the dimension for distance? Nanometers. It could. Be careful with nanometers, because then if you can use nanometers, absolutely right. There's nothing wrong with it. But if I put down nanometers, and we talked about wavelengths of 600 nanometers, for example, then I bet you somebody will now wake up and says, oh, nanometers, oh, I have to put in the wavelengths. Right? You know what I mean? So what you usually use in your experiment is one of these cuvettes, which you have worked with already. Yeah? And they are usually standardized so that the path length is 1 centimeter. So here the unit would be centimeter. Now, big question. What unit is this epsilon? Sorry? It's the coefficient. Does it have a unit? Okay. Does it have a unit? No? Okay. Puzzle for you. No unit equals mole per liter times, I write it in a different way, times centimeter times question mark. So this thing must have a unit that cancels this unit out. Otherwise, we wouldn't get no unit there. So this thing has liter per mole and centimeter. Looks like a weird unit, but hey, life is weird. Okay, so that is the unit for an extinction coefficient. Sometimes it could also be, we could, for example, write mole per liter, the concentration. It could also be, let's say, milligram per milliliter or milligram per liter. Then this unit would become, in this case, liter per milligram and centimeter. It depends on the substance. Yeah? Now, what I can do now is actually, and what you have done in the practical 2 weeks ago, was you measured the concentration of something by measuring the absorbance. How could you do that? Very simple. You put your substance with a given concentration into the spectrophotometer, use the correct wavelength, and measured how much comes out. So you measured the absorbance, and we know absorbance equals concentration times D times epsilon. If we've got D, which is usually 1 centimeter, and if we've got the extinction coefficient, we can very easily calculate what our concentration is. So all we need to do is rearrange this equation and say concentration equals absorbance divided by D times the extinction coefficient. Yeah? So as long as I know the extinction coefficient and I know how long my path length was, usually 1 centimeter, I can measure the absorbance and therefore can calculate the concentration of this stuff in here. Make sense? So I don't have to go along and count molecules. How much is there in this solution? I just simply measure the absorbance at a defined wavelength. This wavelength is incorporated in the extinction coefficient. And if I get an absorbance, presto, I get my concentration. Simples. Right? How do I find my extinction coefficient? Well, sometimes people do what is called, they run a spectrum. Run spectrum. So what they do is they actually measure a defined concentration. So defined concentration with a defined path length, and they measure the absorbance. Remember? Absorbance equals C times D times epsilon. Looks like a euro sign. I heard I shouldn't do something like that post-Brexit. So I do it like properly. So I can rearrange this equation. Epsilon equals absorbance divided by C times D. And I can do that for different wavelengths. So for example, I change the wavelength of every 10 nanometers. So I have here wavelength in nanometer, and here the absorbance. Please note, absorbance has no unit. And what I might see is something like this. This indicates that this particular substance absorbs light very strongly at this particular wavelength. Yeah? Let's say this is 280 nanometers. It can also then absorb light at another wavelength, but for the time being, I'm in this thing here. So 280 nanometers. And if I have a concentration of a known value, I can say, okay, here, this epsilon, I just simply measure the absorbance. I know this, and I get my epsilon in this case. Different substances absorb at different wavelengths. So a characteristic of a protein, for example, proteins usually absorb ultraviolet light at roughly 280 nanometers. This is due to electrons from aromatic amino acids being kicked. What aromatic amino acids do you know? Phenylalanine. What else? Tryptophan. Tyrosine. Yeah? And if you like, histidine a little bit, but not really. It doesn't absorb really in 280. So you can actually measure a protein, the concentration of a protein, by just simply shining light of 280 through it. You measure the absorbance. If you know the extinction coefficient for that, you can calculate the concentration of this guy. Right? Now, in the practical, what you did is you had two different cuvettes, if you remember. One experiment was done with the paranitrophenol at 405 nanometers that had a sort of a yellowish color, the compound. And the other one was done at 280 nanometers. Now we know why we did the 280 nanometers, because that is, you measured a protein concentration, and that is what happened where it absorbed. Paranitrophenol absorbed at 405, but you used two different cuvettes. Why? Very simple. Normal quartz cuvettes, or normal plastic cuvettes, sorry. Plastic cuvettes they absorb light below 380 nanometers. So that means 405 nanometer, the light goes perfectly through, if there's nothing in it that absorbs it. 280 nanometers, the plastic absorbs everything. The light has no chance to even reach the solution. Bong! It hits its little head on the wall of the cuvette. Can't go through. Yeah? That is why you need to have a special cuvette for that can be penetrated by UV light. That's why you had this cuvette with a black dot. Make sense? So whenever you do measurements, you need to make sure that you use the right cuvette. Sometimes before they developed these fairly expensive special plastic cuvettes, they had quartz cuvettes. Quartz, because the mineral quartz does not absorb light in the UV range. Normal window glass does. That's why you can't get a suntan when you lie in your living room and the sun is shining in through the glass. You block out the UV light in the glass or through the glass. If you had windows made of quartz, which would be fairly expensive, I can tell you, you could get a suntan. My advice would be, if you're really interested in suntan and don't care about skin cancer, just simply go outside and grill there, and you save the costs for a quartz window. Okay? Does that make sense, what I described? Now, one more thing, like Apple, one more thing. When we measure these things in a spectrophotometer, we will discuss that then the week after next. We very often look at how much the absorbance is. So absorbance. Again, we know C times D times extinction coefficient. However, when we do that in a spectrophotometer, this absorbance should always be below 1. That's sort of a rule. If the absorbance gets over 1, usually it means it's not very accurate, the measurement. So whenever you use a spectrophotometer, try to keep the absorbance below 1. How could you do that? Loud?
Dilution.
With dilution. We know absorbance equals C times D times epsilon. If the absorbance becomes too high, what you do is you simply lower the concentration here, and as a result, the absorbance goes down. This is sort of shorthand for what's actually happening with the arrows. Does it make sense? So when you do an experiment, I don't want ever to see a result where the absorbance is 2.95. It's just simply, you just as well could pick any random numbers. It doesn't make sense. Does that make sense to you? Yeah? So you should be able to do the quiz on spectrophotometry. You can actually use spectrophotometry to do a lot of fancy things. Like, for example, you can identify compounds with spectrophotometry. But we don't talk about that. That is something that one of my colleagues will discuss with you later on. Any questions? Go in peace. I shall see you on Thursday, where we can do some calculations.